Okay, so we're going to walk through this virtual memory question. So, like any virtual memory or cache question, or even any problem in life, you should always try to keep a close observation of any specs or any extra information that's given to you to solve the problem. So in this case, we're told that we have a 16-bit virtual address space. So what does this mean? Well, this just means we have 16 bits for a virtual address. We have a page size of 4 kibibytes. So what is 4 kibibytes? Well, that's just 4 times 2 to the 10, which is equal to 2 to the 12 bytes. So we have 2 to the 12 bytes worth of data within one page. And next up, we're given 16 kibibytes of physical memory with an LRU page replacement policy. So what is this? Well, this means that we have 16 times 1 kibi, which is 2 to the 10 bytes. So this is 4 times 2 to the 10. We have 2 to the 14 bytes worth of data that can be allocated in our physical memory address space. And we also have a fully associative TLB with 4 entries and an LRU replacement policy. So if you notice, this is typically, what the TLB specs are, aside from the 4 entries. You usually have a fully associative TLB with an LRU replacement policy, but you always want to be cautious if you were, perhaps given, a different type of TLB to work with. Maybe your TLB for whatever reason is direct map or n-way set associative and not necessarily fully associative. But this is typically what you'll see for a TLB. So now that we have all that observed, we can identify what is the maximum number of virtual pages per process. Well, this is easy. So notice it doesn't say the maximum number of pages that a process can have in physical memory, or the maximum number of valid virtual pages per process. It's just asking the general, what is the maximum number of virtual pages per process? So what is the maximum number of pages that you could have for that one process? So if you remember the breakdown for virtual address that we went over in lecture and discussion, so this is our virtual address space. Well, we have 16 bits for our virtual address, if you remember. 16 bits was given to us, and we have a 2 to the 12 byte page size, so we need 12 bits for our offset field, because if you remember the breakdown for virtual address, it goes VPN, then offset. So we need 12 bits because log base 2 of 2 to the 12 bytes is 12. So we need 12 bits for our offset field. And how do we determine how many bits go to our virtual page number field? Well, that's just the number of bits in total for our virtual address space, which is 16, minus the bits dedicated for the offset field, which is 12. So 16 minus 12 is 4. So we need 4 bits for a virtual page number. So if you think about this, well, we have 4 bits for virtual page number. So the maximum number of virtual pages within that process is going to be 2 to the 4, which is equal to 2 to the 4 is 16. So, another thing that you want to keep in mind is, what if they ask what is the maximum number of valid virtual pages per process? Well, that's going to be completely dependent on your physical address space. So now, how many bits wide is the page table base register? Well, if you think about the page table base register, well, what is the page table base register? All it is it's a register that holds the address of your page table. So I talked about this during the review session, but if you think of your page table, we think of it as two-dimensional, but really it's just data. It's just a giant table of data that's laid out in your memory. And if you think of your memory as kind of an infinite array of mailboxes, so it has a bunch of addresses and data at each address. Maybe there's some data there, some data there. That's all memory is. So your page table for a process is located in memory, if you recall. So if it's located in memory, well, that means it has an address, and that's exactly what the page table base register stores. So all the page table base register is it's the register that stores that address. And since this address is in physical memory, the bit length for a page table base register is just the bit length of an address in physical memory. So if you look at this, well, how many bits do we have in physical memory? Well, that's just going to be what is that? It's just going to be 14 bits because we have 2 to the 14 bytes worth of data. So you need 14 bits to identify where in physical memory your data is located in, because log base 2 of 2 to the 14 is 14. So you need 14 bits for any given address in physical memory. So your page table base register, since it's the address of the page table located in physical memory, that's just going to be 14. For question C and D, let's look at everything that's provided for us. Well, only the code and the 2 arrays take up memory. The arrays are both page aligned. So what does this mean? Well, they both start on a page boundary. They start at the beginning of a page. The arrays are the same size and do not overlap. So these 2 pieces of information are both highly crucial. You want to keep those in mind. Also, all of the code fits in a single page, and this is the only process running. So what do we get from this? Well, we know that of our TLB entries, one of them is dedicated for code. So tying back into our TLB entries, well, how many do we have? If you remember from earlier in the problem, we have 4 entries total. So we're given this code, sorry about that. So we're given this code, and it's scale and copy. And if you look at it, well, we essentially have 2 arrays of integers. So we have base and copy, and we have a number of entries, so the number of entries, and some scalar. And all we're doing right here is we iterate through every element, and we take the data at base, so the ith integer of base, and we scale it up and store that into the ith element of copy. So the next question, if scale and copy were called on an array with n entries where n is a multiple of the page size, how many page faults can occur in the worst case scenario? Well, we know that the TLB has 4 entries, and I just want to emphasize that the TLB itself does not have the data of those pages. All the TLB has is virtual page number to physical page number mappings, with permission bits. So the data really isn't located within the TLB. However, I'm going to draw the data corresponding to each TLB entry. So don't mistake that. I feel like this is a significantly easier way to see and approach these problems, but it's important to keep in mind that the TLB does not store the data of each page. It might have the metadata like permission bits or the mappings, but it doesn't have the actual data values. So in our TLB, we have 4 TLB entries. Well, we know that 1 has to be dedicated for code. And we know that both base and copy start on page boundaries. So one page is where base starts at the beginning right here, and then we have copy, which starts at the beginning of another page, and they don't overlap. So notice that there's one page, and it essentially is kind of wasted. If we have the next page dedicated for the next n elements of base, well, we can't have another page dedicated for the next elements of copy because we've already breached our capacity of 4 entries. So at any given point, you can see that there are going to be 2 pages dedicated for copy and base, for the values we're trying to read. So in the worst case scenario, how many page faults can occur? Well, in the worst case scenario, our TLB is cold. Sorry about that. Our TLB is cold, so we have to reload in all our mappings and all our data into memory. So in the worst case scenario, well, we're going to have 1 page fault for sure, because we have to load in code, that occupies 1 page, and it's not going to be in our TLB, so we need to undergo that 1 page fault. We end up going to the TLB, we miss, that goes to the page table, and we don't have a valid mapping, so we have to load that in from disk into our TLB and page table. So we have 1 page fault for code. And what else? Well, how many page faults can occur in the worst case scenario for base and copy? Well, if you think about base and copy, they're both the same size, so they both have size n. And let's take a look at our stride. Well, we're striding by 1 integer. So 1 integer is 4 bytes. So, how many integers are in 1 page? Well, we're told that we have a 4 kilobyte page size, which is just 2 to the 12 bytes. So, of the 2 to the 12 bytes within a page, we're taking a stride of 4 bytes because 1 int. So this means that we're accessing 2 to the 10 elements within one page. So, if our entry spans n elements, every 2 to the 10th element we're going to have a page fault. It won't be in the TLB, and because this is the worst case scenario, it won't be in the page table as well. So this is just for one array, and we have 2. So 2 arrays for every n elements, or for every 2 to the 10 elements within our n element array, we're going to have a page fault. So what is this value? Well, this is just equal to 1 plus n over 2 to the 9. Okay, so the next question, we're given a different case scenario. So what about the best case scenario? Ooh, that was really difficult. What about the best case scenario? Well, in the best case scenario, everything that we're trying to load or trying to access is already loaded in our TLB, our page table, or our cache. That's just always going to be the best case scenario. So in the best case scenario, how many iterations of the loop can occur before a TLB miss? Well, let's go back to the TLB. So we have one entry dedicated for code, we have one entry dedicated for base, and we have one entry dedicated for copy. So if you think about this, well, how many int elements are in one page? Well, it's 2 to the 10. So 2 to the 10 int elements in a page. So let's say that we, everything is loaded in and we iterate through this loop 2 to the 10 times. Well, what about the 2 to the 10th plus 1th time? Well, the next time we try to iterate this loop, we need to access the next element of base and the next element of copy. And those are both located on separate pages that aren't in the TLB. So, well, what happens here? Well, we try to access the next element of base. So, let's say in the best case scenario, base 2. So the second page that we need to hold the data for base, let's say it's already in the TLB, right? Well, what about the second page of copy? Notice that it's not there. There's no physical way that we can fit in more than one page of base and more than one page of copy. So corresponding pages, we can't fit more than one pair at a time because that already takes up half our TLB. Notice that we already have 3 pages dedicated for our first 2 to the 10 iterations, but we can't iterate even one more time because we can't have 2 pages in one page at the same time. So the maximum number of iterations that can occur until a TLB miss in the best case scenario, it's just going to be 2 to the 10.